Hello, welcome back. The title of this lesson is called Avogadro's Number and the Mole. This is part one. Honestly, one of the most fundamentally important lessons in all of chemistry. What we're going to do is define this number called Avogadro's number, and we're going to talk about why we use it in chemistry. But let me just give you the punchline in the beginning so you know the roadmap of where we're going. Avogadro's number, it allows us to start to do quantitative calculations in chemical reactions. Because as you know, everything's made of atoms, but atoms are so small that you can't really individually count them. So the problem is when we do a chemical reaction in a lab, we want to measure out so much of material A and so much of material B and react them together and figure out how much of material C is going to result from the chemical reaction. But when we measure things in the lab, we're always measuring them in terms of their mass, in terms of grams. Grams of carbon, grams of oxygen. How much carbon dioxide in grams will we form at the end of that reaction? Avogadro's number is the tool that we need to join grams, which is something we measure in mass, with molecules and atoms, which is what we know everything is made of. Let me say that one more time, because it really is the punchline to why we are doing this. I want you to know why before we jump into it, okay? Avogadro's number is the tool to join the microscopic, counting atoms and molecules, with the macroscopic, which is measuring grams of a substance, okay? Joining those two ideas together, we have to do it in order to calculate anything. All right, so let's talk about Avogadro's number. Now, let's put that aside for just a second and talk about something familiar to you, right? So let's say you have chickens and you make the chickens make a bunch of eggs, right? So let's say you're a very prolific chicken, a chicken person, and there are thousands of eggs in the chicken coop, okay? Now, we can count all the individual eggs. The eggs will be like the atoms, but when you get to have so many of them, it's very difficult to count them. So what we do is we invent a new measurement, a new number that is what we often use to buy and sell eggs. We call it a dozen. So you know that a dozen eggs, the word dozen, it means 12 eggs. But the word dozen doesn't have to apply to eggs. We could have a dozen rocks. That means 12 rocks. We could have a dozen marshmallows, a dozen pencils, a dozen pennies. But you also know that you can have multiple dozens. If I tell you I have 5 dozen of something, then you know it's 5 times 12, 60 quantity of something. Or 6 dozen. Actually, you can even have fractions of a dozen. What is half a dozen? Half a dozen is a fraction of this new unit we call a dozen. Half a dozen is 6. So you can invent a new unit that helps us count very large numbers of objects. In this case, we're just talking about eggs, and a dozen is not so big, but it's a helpful everyday quantity. So we know that when we have 12 of something, we can refer to it as 1 dozen. But as we just said verbally, we can have 2 dozen of something or 5 dozen of something. You can have half a dozen of something, which would be 6. You could have 2.5 dozen, which would be, we could calculate what that would be. We could have 100.7 dozen of something, and we could calculate what that would be. So now let's tie this quantity, because it really is this concept, because it really is exactly the same thing, to the concept of Avogadro's number. Now, most important things in physics and chemistry and math are named after people. You could look up the history of Mr. Avogadro, did some very fundamental work in chemistry. And this is not a history lesson, but it's fascinating to see how people figured things out. Well, this number is named after a person, Avogadro, okay? Now, what we are going to do first is we're going to write down what Avogadro's number is, and then I'm going to tell you how we use it. And I'm going to tell you how that relates to the concept of the mole, which is very closely related. So Na means number, Avogadro. It's just Avogadro's number. That's all that thing means. And it's defined to be 6.02. You're like, oh, that's not so big. 6.02, but it's times 10 to the 23rd. This is Avogadro's number. So when you define Avogadro's number, Na, that's Avogadro's number. If you ever see this in a book, this is what you substitute in your mind. 6.02 times 10 to the 23rd. Now, before we jump any farther, let me just also tell you that you also may see it in some books as 6.022 times 10 to the 23rd. So whatever book you're using, you're going to either see this or this. Of course, this is the more accurate version of the number, but for everyday chemistry calculations, you could just say 6.02 times 10 to the 23rd. Sometimes in my calculations, I'll put the extra 2 there, but honestly, it won't matter much in the final answer. Why? Because Avogadro's number is enormous. It's actually impossible for any of us to really understand how big Avogadro's number is. Think about it for a minute. What you're saying is you take this decimal point, if you move it 1 spot to the right, 2 spots to the right, then that would be 602. But I'm not moving it 2 spots to the right, I'm moving it 23 positions. I don't even want to waste my time writing that out, but that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's 23 movements of the decimal. I don't even have a word to describe that. I know what million is. I know how big that is. I know what billion is. I know what trillion is. I'm sure there is a word to describe something that big, but I don't know what it is without looking it up because I never use numbers that big. Avogadro's number is truly enormous. So enormous that I can't even visualize what an Avogadro's number worth of something would be. But that's okay, because you see, atoms are so small, I can't visualize that either. I mean, I know that they're small, but conceptually, how small? I don't think any of us can really understand how small an atom actually is compared to an everyday object. That's why Avogadro's number is so big, because we're counting atoms. Just like there's 12 eggs in a dozen or 12 sticks in a dozen sticks, well, there are this many Avogadro's number in what we call a new unit of measurement called the mole. The mole is what we talk about. The mole is the counting unit equivalent to it or similar to a dozen. And the number attached to the mole of a quantity of a mole of something is 6.02 times 10 to the 23rd atoms or molecules or whatever it is we're discussing. That's how many individual objects there are. So let's write that down, because just the actual number is written on the board right here. But we have to use this number, so we're going to talk about the concept of the mole. Now, mole is only 4 letters long, but we actually abbreviate it in chemistry, and we call it MOL. So we don't ever write it out MOLE, we write it as MOL. And these ideas are fundamental to chemistry. We use them in every problem that you do because we have to use moles. We'll talk about why, but we have to use moles to calculate pretty much anything in chemistry. So what is a mole anyway? 1 mole of any substance you can think of. 1 mole of carbon dioxide, 1 mole of carbon monoxide, 1 mole of sodium chloride, 1 mole of sugar, 1 mole of anything in chemistry, right, is equal to 6.02 times 10 to the 23rd. And what are we talking about? 1 mole is 6.02 times 10 to the 23rd? Well, it's objects. And the reason I put objects here is because the mole, the number 6.02 times 10 to the 23rd, that never changes. That is like 12 objects in a dozen. In this case, it's just a much bigger number because we're counting atoms, which are small. So the fundamental quantity, instead of 12 items being a dozen, we say a mole. That's the counting number. That's the new unit we're coming up with. 6.02 times 10 to the 23rd what? Well, it depends on what you're talking about. If it's just atoms of lead, then it's 6.02 times 10 to the 23rd atoms of lead. That's how many atoms are there, right? If it's water molecules, then it's 6.02 times 10 to the 23rd molecules of water. Because remember, a molecule of water is a individual thing. These are bound together and they're floating around as a discrete object. So if I have a mole of water molecules, one of these things is just 1 water molecule. I would need 6.02 times 10 to the 23rd of these water molecules to exist in a mole. Okay, but if I'm talking about, any object, a mole of dogs, I mean, you can have a mole of dogs. It's just going to be a very large number of dogs. Okay, very large number of atoms, very large number of molecules. So let's write down what we're saying. That's why I keep it general. 1 mole of anything is this many objects, whatever the heck it is you're talking about. So let's give some examples. 1 mole of carbon, but let's just be specific and call it carbon 12 atoms, because carbon is an atom, it's not a molecule, is how many of these atoms? Well, it's a mole of it, so it has to be 6.02 times 10 to the 23rd atoms. Atoms what? Atoms of carbon-12. Remember, I'm just going to remind you that carbon lives in the periodic table right here, atomic number 6. Carbon has 6 protons in the nucleus, and the most stable form of carbon also has neutrons, of course, 6 neutrons. 6 plus 6 is 12. So the most common form of carbon that exists in nature is carbon-12. So whenever I write carbon down with the 12 up top, I'm telling you this is the most common form of carbon in nature, but there are occasionally a carbon atom in nature with 1 or 2 extra neutrons in the nucleus. So that would be carbon-13 or carbon-14. Those are extremely rare. So when I'm counting, I'm just explaining and reminding you of something that you should already know from the past. When I write this down, I'm saying this exact form of carbon with 6 protons and 6 neutrons, when I have a mole of those things, of these atoms, that is this many atoms. And so what we're talking about is atoms, so the mole refers to the number of atoms. However, what if I'm talking about a mole of water molecules? We know that water is a molecule. It is a structure that is composed of 2 hydrogens and 1 oxygen. So there's actually 3 atoms inside of there, but they're bound together in a discrete unit. So if I have a mole of these things, it's not atoms we're referring to. It's 6.02 times 10 to the 23rd molecules. And note, that's why when I defined the mole, I said it was 6.02 times 10 to the 23rd objects, because what it is the number is the counting object, like I just said, right? I just said you can have a dozen eggs, that's 12 eggs. You can have a dozen frogs, that's 12 frogs. I could have a dozen buffalo, that's 12 buffalo. So it's really a dozen is 12 objects. Well, a mole is 6.02 times 10 to the 23rd objects, and it just depends on what you're talking about. If you're referring to individual atoms, then it's this many atoms. If you're referring to molecules, then it's this many molecules, right? One more example. 1 mole of, instead of a molecule, NO3 ion. This is a polyatomic ion, right? So 1 nitrogen, 3 oxygens, where the overall thing has a charge of -1. But I'm talking about 1 mole of this entire thing here. So how many do I have? 6.02 times 10 to the 23rd, what? Ions. Which is a grouping of these things. Just like the water is a grouping of these things, the ion, the polyatomic ion, is a grouping of these things. I have this many, which is a huge number of them when I have 1 mole of them. All right, so we've talked about Avogadro's number is just the number, 6.02 times 10 to the 23rd. We said that in books, sometimes you'll see 6.02, sometimes you'll see 6.022 times 10 to the 23rd. You can use whatever number you want in your calculations because that 1 extra digit won't matter very much. I will do it both ways, probably. We said that 1 mole of an object is that many, which is a huge number of fundamental objects. If you're talking about atoms, then it's that many atoms. If you're talking about molecules, it's that many molecules. If you're talking about ions, it's that many ions. It's the same concept no matter what it is you're talking about, right? So now I want to take just a second to talk to you about where this fundamental number called the mole actually comes from. Now, in life, we have to have some fundamental standard. We have to have some reference point. When I am driving from my house and I want to know how far away I am, I'm measuring it relative to my front door from my house. That's the reference point, right? If I'm building a submarine and I want to go down below the water, I want to know how far down below the water I'm going. I have to have a reference point. The reference point is the surface of the water. So I'm going down below the water. That's my reference point. In chemistry, we need a reference point too, because we're talking about atoms which we can't see with our naked eye, which are so tiny and so numerous. We need a new counting unit called this mole. And this is going to allow us to do calculations with chemical reactions. You have to trust me on that. We're going to get there. All right. But where do we come up with this number? Why is it 6.02 times 10 to the 23rd? Why isn't it 6.05? Like 12 is a dozen eggs. Why couldn't 12 be 15? Why couldn't a dozen mean 15 eggs? I don't know. There's some person a long time ago. There's probably an awesome historical reason that would be interesting to learn why a dozen is equal to 12. But for Avogadro's number and the mole, we know the reason why, and I'm going to teach you the reason why it's 6.02 times 10 to the 23rd objects. And the reason is because we have to have a standard. We talked about standards, and every measurement system has to have a standard. On this periodic table, we need to pick some element that's going to serve as our standard mass. And you want to pick one that is very common. You want to pick one that we interact with all the time. And you want to pick one that's very stable, that doesn't decay radioactively or anything like that. And we're going to have that as our standard. Hydrogen, you know, it has pros and cons, and all these elements over here would be good choices. But chemists use the element carbon for the standard. If you remember back, we talked about atomic mass units, and we said the same thing. Carbon served as the standard. So when it comes to Avogadro's number and the mole, same thing. Carbon serves as a standard. So where does Avogadro's number come from? We'll just write it down here. I'll put definition of the mole, right? And this is a definitional thing. This is just, we have to pick something that exists everywhere that we can measure with great precision to serve as our standard. So what we say is that 1 mole is the number of atoms in exactly, and I'm going to underline the word exactly, in exactly 12 grams of pure carbon-12. And remember, when I say carbon-12, I mean this is the most common form of carbon in nature, with 6 protons, 6 neutrons, extremely stable. It's in life, it's in our bodies, it's everywhere. We can measure it with great precision. So what we are basically saying is that I'm asking the question to you, why is a mole 6.02 times 10 to the 23rd? Why isn't it times 10 to the 25th? Or why isn't it 6.5 times 10 to the 23rd, or just some other number? Why is it the number that I wrote on the board? The reason is because it's not pulled out of thin air. The mole is defined to be the number of atoms in exactly 12 grams, as good as we can measure it, of pure carbon. Pure carbon, and this form of carbon, which is the most common form of carbon. And that means that this is 6.02 times 10 to the 23rd atoms of carbon-12. This is the most common form of carbon in your body, right? With 6 protons and 6 neutrons. So what happens is they just pick an element off the periodic table that we are going to use as our standard. We pick carbon, and life is made of carbon, very stable, very common. And then we're going to have to pick a known quantity of carbon. We're going to pick 12 grams. That's not a coincidence. We're going to tell you in a minute why we picked 12 grams of carbon. Why not 7 grams? Well, there's a reason. 12 grams of carbon. And then we're going to count, we're going to measure scientifically and experimentally how many atoms of carbon are in that sample of 12 grams. And experimentally, when you measure how many atoms are in a 12-gram sample of carbon, pure carbon, this is the number that we come up with. So this is done by experiment. And of course, every year they measure it and it gets more and more accurate. There are more digits beyond the 6.02. I already told you, sometimes you can say 6.022 times 10 to the 23rd. And so the number can get more and more accurate, you know, the more with the higher precision you can measure it with. Okay? But what this basically says is the following. If we know that this is true, this is the definitional thing. Take some pure carbon, find 12 grams of it, measure it as accurately as possible, and somehow experimentally measure how many atoms there are. This is how many. We're going to call that 1 mole. So what we have figured out is that 1 mole of carbon-12, which is that version of carbon we're talking about, is equal to 6.02 times 10 to the 23rd atoms of carbon-12, right? That's exactly what it means. But that's also exactly equal to 12 grams of carbon-12. I need you to read this line a couple of times because we're going to use this in the next couple of lessons. 1 mole of carbon is equal to this many atoms of carbon, which is also equal to 12 grams of carbon. This is just a restatement of what I wrote here. 1 mole is the number of atoms in exactly 12 grams of pure carbon. So 1 mole of carbon is this many atoms of carbon, but that's the same thing as 12 grams of carbon. But you see what we've done here by picking something from the periodic table, who, by the way, whose atomic mass and atomic mass units is exactly 12 atomic mass units of that isotope of carbon. What we've done here is we have linked the microscopic in terms of atoms to the macroscopic in terms of grams. I said that in the beginning. That's why we're doing this, because we can't count atoms in the lab, but I can measure grams. I can measure 12 grams of carbon. I can measure 16 grams of carbon. And this can serve as a conversion factor. This can serve as a conversion factor, like there are, however many centimeters in a meter, 100 centimeters in a meter. That's a conversion factor to go from meters to centimeters. Here, we've written down a conversion factor that relates something what we call the mole to something that we call number of atoms to something that we can actually measure in the lab called grams. That's what you measure on a balance, right? And so this conversion factor is what we use later with chemical reactions, with the balanced chemical reactions, there, because I'll tell you another secret a little bit ahead of time. You remember the balancing of a chemical reaction, right? I'm just getting ahead of myself a little bit, but I can't help but try to tie it together, right? When you make water, here's H2, here's O2, and it yields H2O. Now this is not a balanced chemical reaction because there's not enough oxygen, right? So there's 2 oxygens here, so I have to put a 2 right here, but now I have 4 hydrogens, so I have to fix that right here. This is balanced, 4 hydrogens, 2 oxygens, 2 oxygens. This is balanced. This is a chemical reaction. These numbers in front, I have been telling you that they're coefficients for the molecules. This is saying 2 molecules of hydrogen gas plus 1 molecule of oxygen gas will yield 2 molecules of water. That is true. I did not lie to you, but these coefficients also are the number of moles involved in the chemistry. What this is saying is 2 moles of hydrogen, where a mole is this, 2 moles of hydrogen gas plus 1 mole of oxygen gas yields 2 moles of water. Because a mole is a measurement of the number of molecules, right? So it's just a multiple of a single molecule. So those coefficients refer to molecules, but those coefficients in the chemical reactions also refer to the moles. So you see how we're starting to tie it together. We can write down a chemical reaction. We have the coefficients in front of the balanced chemical reaction. They refer to the number of moles participating in the reaction, the number of moles. But we can relate the number of moles of anything to the number of atoms of the substance. And in the next lesson, I'm going to show you how we've done it for carbon here, but we can relate the number of moles to the number of grams of any of these substances. So you can use a chemical reaction to calculate the grams of a product, or the grams of a reactant, or the grams of anything, because that's what we measure in the lab, grams, in terms of mass. We can't count molecules, we have to measure mass of something. That's why we learn Avogadro's number. It is the counting number, similar to a dozen, which allows us to convert from, essentially into grams, so that we can do the actual calculations in terms of things we can measure in the lab. All right, we're gonna do a couple of problems, but one more time, 1 mole of carbon atoms is equal to this many carbon atoms, which is equal to 12 grams of carbon atoms. So now what I want to do is I want to solve a couple of, I think, pretty simple problems, but in the beginning, these things don't seem simple because you're just learning it for the first time. So if you don't get it right away, that's fine. We all have to learn about this. I remember having trouble with moles when I learned it. So let's go together and solve a couple of quick problems. I want you to state true or false if the following statement is true or false. So let's read the statement. Here's the statement. You have a mole of dogs. You also have a mole of dog legs. True or false? Right? Well, what is a mole of dogs? And let's just write it down. That sounds weird, right? But what is a mole of dogs? 1 mole of this thing called dogs. All right, 1 mole of dogs. Well, that means I don't have 1 dog or 2 dogs or 3 dogs or 4 dogs or 5 dogs. I have 6.02 times 10 to the 23rd dogs. That's what it means. That's 6.02 times 10 to the 23rd. That's an enormous amount of dogs. I don't even think there are that many dogs on the planet. I know there aren't, okay? But if I had that many dogs, that's what it would be. So if I have a mole of dogs, I also have a mole of dog legs. Is that true or false? Well, think about it. Every dog actually has 4 legs. So if I have this many dogs, an enormous amount of dogs, I have to have 4 times that many legs. So if I have a mole of dogs, I do not have a mole of dog legs because I have to have 4 times as many legs, which is more than more than a mole, right? It's 4 moles. So basically I would have 4 moles of dog legs, essentially, because I have 4 times that many. So the answer to this, if I have a mole of dogs, do I have a mole of dog legs? That is false, right? That's false. Let me take you through the logic there. It's a little bit of a weird question, but it gets us thinking about in terms of, I mean, another way to say it is, let's throw away the confusion of the idea of mole. Let's just change mole to something else. Okay, here's the next question. It's not a real question, right? But let's just talk about it. Here's true or false. You have a dozen dogs. Do you have a dozen dog legs? Well, no, you know the answer's crazy. If you have a dozen dogs, that's only 12 dogs. So you have 4 times that many legs. You don't have a dozen dog legs, you have 4 times that many. Same thing with the moles. If I have a mole of dogs, I don't have a mole of dog legs, I have 4 times that many. That's why it's false. Okay, problem number 2. True or false, there are 2 moles of ions contained in a mole of solid sodium chloride, NaCl. True or false, there are 2 moles of ions contained in sodium chloride, NaCl. Well, what do we say we have? This problem says that we have 1 mole of NaCl. Now, this is an ionic compound. You all know sodium is on the left, chlorine is on the right. This is an ionic compound, right? It's a formula unit, essentially. This is a 3-dimensional lattice where the ratio is 1 sodium to 1 chlorine in the crystal, in the 3-dimensional crystal. But what does this actually mean? How many formula units do I have? Well, I have 6.02 times 10 to the 23rd. I'm going to put formula units of NaCl. In other words, maybe I have a sugar cube that's exactly 1 mole. If I could zoom in, I would see a 3-dimensional lattice of sodium chlorine ions bound together, right? It would be a ratio of 1 to 1. Sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, all in 3-dimensional space. And I would have this many 6.02 times 10 to the 23rd groupings of NaCl, because that's the formula unit. That's the fundamental ratio, 1 to 1. Sodium to chlorine, 1 to 1. How many of those groupings of 1 to 1 do I have? I have that many, 6.02 times 10 to the 23rd of those things. The question is, are there 2 moles of ions contained in a mole of sodium chloride? Well, if I have 1 mole of sodium chloride, what is sodium chloride? Well, it's sodium ions and it's chlorine ions. This wants to lose an electron, this wants to gain an electron. So 1 mole of this thing contains both of these. So if I have 1 mole of this grouping, then therefore I must have 1 mole of sodium ions, and I must also have 1 mole of chlorine ions. So the question is, literally, or verbatim, there are 2 moles of ions contained in a mole of solid sodium chloride, true or false? Well, in 1 mole of this formula unit, I have 1 mole of this and 1 mole of this. Therefore, I have 2 moles of ions. So the answer to the question is true. This one is true. Now, you can probably more easily verify this if you just talk about dozens. All right, let's change it around again. You have a dozen sodium chloride formula units. True or false? You have 2 dozen ions. Well, you know if you have a dozen sodium chloride units, then you have a dozen sodiums and a dozen chlorine ions, and so you have 2 dozen ions. So it makes sense when you talk about dozens. You just have to get used to this idea of a mole just being a much larger grouping than a dozen. That's it. So this one is true. 1 mole of sodium ions, 1 mole of chlorine ions, 2 moles of ions altogether. All right, so we're done with that problem. Let's turn our attention to something a little more quantitative. They're not hard, but something a little more mathematical than what we've done, which are conceptual. All right, here's the question. Given the following formula, or the formula for sucrose, which is C12H22O11, sucrose, answer the following. Here is the first one. How many moles of carbon are in exactly 1 mole of sucrose? And the second one is how many atoms of carbon are in exactly 2 moles of sucrose. So here's the thing. When you're asked how many atoms are in 2 moles, or how many moles are in this, or anything like that, then you need to stop trying to get the answer in your head. You just need to stop. You have to learn how to use dimensional analysis and unit conversions in chemistry properly, because they are going to save you long term. In fact, I can honestly say that is the absolute number one most important piece of advice. When you're doing chemistry, don't try to get the answers in your head. You're just going to get confused. I can't do it. So, I mean, I'm not saying I'm the most smartest guy in the world, because I'm not, but I don't think most people can do it in their head. And even if you can, eventually you're going to get a problem that's too complicated for your head. So even if you think you know the answer, don't do it in your head. Let's write it down properly. So what we have is sucrose. We're saying it's C12H22 and then O11. Now the problem is asking us how many moles of carbon are in 1 mole of sucrose. So just like if I ask you to convert between meters and, I don't know, centimeters or whatever, and you're doing a unit conversion, you need to write down what you are given in the problem statement. So in chemistry, that's what you write down first. You were told there are 1 mole of sucrose, so you write it down. 1 mole, and you don't write the word sucrose, you actually write the formula, C12H22O11. All right, so you've written down what you know is true because this is given to you in the problem statement. You have 1 mole of this. Now, this is more complicated than water, but it's basically a large number, Avogadro's number, of this molecule. And you're asked in the problem, how many moles of carbon are in there? How many moles of carbon are in there? So you have to do a unit conversion. In order to cancel anything, you have to write the same thing on the bottom, the same unit on the bottom. So 1 mole of C12H22O11, and you're trying to get to the final destination of how many moles of carbon. So in 1 mole of this, which is 6.02 times 10 to the 23rd of these things, in 1 mole of this, how many moles of carbon do you have? You have 12 moles of carbon for every 1 mole of this. Why? Because in 1 sucrose molecule, there are, in 1 molecule, you have 12 carbons. But in the next molecule, you have 12 more carbons. In the next molecule, you have 12 more carbons. Next molecule, 12 more carbons. So in 1 mole of these things, you have 12 moles of carbon 12. Right? Make sure, or I guess I'll just, sorry, not carbon 12. I don't want to write it down like that. 1 mole of carbon. Right, 12 moles of carbon, sorry. How do I know it's 12 moles of carbon? Because there's a 12 here. Because for every 1 grouping I have 12 carbon atoms. So if I multiply and I have 1 mole of these groupings, I must have 12 times the amount of actual individual carbon atoms. So in another way of looking at it is, if you want to talk about it, if I have 1 dozen of these, then I would have 12 times that in the number of carbons I have. It's the same thing, it's just dozen is replaced by the word mole. And when I arrange it like this, instead of upside down, I do that because I can cancel moles of sucrose with moles of sucrose. The only unit I have left is moles of carbon. Is that what they're asking? How many moles of carbon in exactly blah, blah, blah? You arrange it so that the unit you have left is the only unit left. So that is the answer to the calculation. So all you have to do to figure this out is you take the 1, multiply by 12, divide by 1, and so you get 12 moles of carbon. Now ask yourself, does this make sense? Well, if I have 1 mole of sucrose, 1 mole of that big molecule, that 6.02 times 10 to the 23rd, I have to have 12 times the amount of carbon 12 times the moles of carbon, because moles of carbon would be referring to the atoms of carbon. But I have 12 atoms of carbon for every one of these big things. So if I have 1 of the mole of these big things, I must have 12 moles of the carbon atoms. And that's what the unit is left over. I could put the word atom if you want to. The next thing I will say is that when you're writing down your units, you have to write moles of, and you have to write down the formula. Moles of formula. Moles of whatever it is, carbon atoms, to make sure you don't get confused. So this is 12 moles of carbon atoms, right? Because the problem statement says how many moles of carbon, and that means carbon atoms are in, the problem statement there. All right, next problem. Same thing though, sucrose. How many atoms of carbon are in exactly 2 moles of sucrose? So even if you don't know what to do, you write down what you know. You write down that I have 2 moles of sucrose, but I don't write down the word sucrose. I write down C12H22O11. I have 2 moles. This is like 2 dozen of this thing, except the dozen is replaced by a mole, which is much, much bigger in terms of the number. Right, now where am I trying to go? I'm trying to figure out how many atoms of carbon I have. Atoms of carbon. So I have to do enough unit conversions to get there. Now, I don't know how to go directly to atoms. However, I do know that I can convert from moles. Here, 1 mole of this stuff, C12. Got to write it down so it matches perfectly. 1 mole of this, I can say, is equal to 12 moles of carbon. This is correct. I know this is correct because I just did this in the last lesson. If I stop the conversion factor here, then I'm going to calculate how many moles of carbon I have. But I don't want moles of carbon. I want to know how many atoms of carbon. So I have to continue the unit conversion, and I have to say, because I want to cancel the moles, I know that 1 mole of carbon is 6.02 times 10 to the 23rd. And here I guess I'll start to, in my notes usually I carry an extra decimal, so I guess I'll start doing that. 6.022 times 10 to the 23rd, and this is carbon atoms. Right, because that's what a mole is. 1 mole of carbon is 6.02 times 10 to the 23rd fundamental units of whatever it is you're talking about. In this case, carbon refers to atoms. So it's that many atoms. And so when we do it this way, 1 mole of carbon cancels with this. And so the only unit left that we have is carbon atoms. So make sure you understand, it's a 2-step unit conversion. You're converting from moles of sucrose to the moles of carbon, which are the individual atoms in the sucrose. Then if we stop the calculation there, we have moles of carbon, but we know that every mole of carbon is this many atoms, so we multiply again. And then you don't have to think, do I multiply or do I divide? That is going to get you into trouble. Don't try to logically think about that. You cancel units until you get to where you're trying to go. So to finish this out, you take 2, multiply by 12, divide by 1, multiply by Avogadro's number, 6.02 times 10 to the 23rd, and then divide by 1, and then what you will get as an answer is 1.445 times 10 to the 25 carbon atoms. So you see how we're able to use the concept of a mole to start to calculate how many atoms are in a substance. And later we're going to join it into grams so that we can calculate grams of a substance in a chemical reaction. If you don't get it, okay, if you don't see the unit conversion, that is just because it's an unfamiliar quantity, right? It's an unfamiliar idea, and you just need to see it several times in order for it to sink in. So let's go and do that. Let's see, where do I have space? I guess I can do it probably right down below. We have one more. I think we can fit it in down here. So we'll do it right down here. Here's our last question for this lesson. And then, of course, the next lesson we're going to have additional. Here we go. What number of moles of hydrogen atoms are there in the following substance? 0.08850 moles of C4H10. So I want to know how many moles of hydrogen atoms are in that quantity of that substance. So what you do is you write down that what you're given in the problem statement. You were given that it's 0.08850 moles of C4H10, right? And the question is asking, how many moles of hydrogen atoms? How many moles of hydrogen atoms are there? Well, I know that 1 mole of this stuff, C4H10, how many moles of hydrogen atoms will there be in there? Well, there has to be 10 moles of hydrogen atoms in there, right? And then what does that do? That cancels the moles with the moles, and so the only unit you have left is the unit that you're trying to calculate, the number of atoms. Why do we do it this way? Because if this is the substance, think about it in terms of dozens, right? If I had a dozen of these things, how many hydrogen atoms would I have? Well, I would have 10 times that amount. I would have 10 times that amount, because every, in terms of hydrogen atoms, because I know that for every one of these groupings of molecules, there's 10 hydrogen atoms. So that means for every 1 mole, which is a big number of these things, there must be 10 times the amount of hydrogen atoms. Because the fundamental unit for this is a molecule, and the fundamental unit for the hydrogen inside is just the atom. So since there's 10 of them here, there has to be 10 times the amount of atoms as there are moles of the parent substance there. Okay, so what do? We take 0.08850, we multiply by 10, we divide by 1, and then what we get is 0.885 and the unit left over is moles of hydrogen. And I don't need to write hydrogen atoms because I know that when I'm talking about moles of hydrogen, hydrogen is just a hydrogen atom in the molecule, so we know it's atoms we're referring to. Whereas before, when I say mole of this thing, you know it's the whole molecule it's talking about, because mole is kind of a fluid thing. Mole is referring to either atoms or molecules, and the molecules can of course be big or small. There's all kinds of variation here. So when I'm talking about a large substance like a molecule, that's mole refers to that many of those things. And then on the inside, when I'm talking about mole of hydrogen, then of course it's the atoms in there. And so that's what's going on. So for every 1 mole of this molecule, there must be 10 moles of the smaller thing called the atom on the inside. So we set that conversion factor up to cancel what we don't want. This idea of canceling moles and molecules and things, you have to get used to it. If it seems a little foreign right now, it seems a little bit rough around the edges, that's okay, because it's a new substance. It's a new concept is what I'm trying to say. So what I'd like you to do is solve these yourself. Start over, watch the lesson again. Solve these yourself. Make sure you can write these unit conversions down yourself. Don't just watch me and say, oh, I got it. You need to write it yourself. So do it yourself. Then follow me on to part 2. We're going to get a little more practice with doing some basic calculations involving moles and molecules and atoms of a substance.